Able to see it? Yes,
Yes,
or
sir.
no? Yeah. Just a second. It's got stuck. Okay. So last class we were seeing, right, this particular equation. Finally, we have VF for ideal MOSCAP, VFP flat band voltage. That is the condition where bands are flat inside semiconductor corresponding to zero charge inside semiconductor, which means zero charge throughout. Okay. So and that is VFP equal to 0. So there is another voltage limit we saw, that is VT, threshold voltage we called it. And that is basically the voltage corresponding to the onset of inversion we said. And we wrote these equations. VT equal to psi ox plus is. This equation is valid only if it is ideal MOS junction. It gets modified if it is non-ideal. So the voltage drop is falling across oxide and semiconductor. That's what it means. Okay. So nothing great in this. Just summing up voltage drop across oxide, voltage drop across semiconductor, which is the voltage outside, that is seen outside. So basically, this is simply from Kirchhoff's KVL. Okay. So then psi ox is first derived. It is minus QS by C ox. This is coming from Gauss's law. Electric field comes from Gauss's law with QS inside semiconductor, and integrate it, you get psi ox. So psi s, we said at inversion, it is 2 VT ln PP naught by Ni, so equal to 2 phi f, where phi f is called Fermi potential, that is with reference to EI. All right. So this Fermi potential. Difference to EI only. So don't get confused with any other potential. So QS is minus QNA XD, and XD is given. So, but let us, before moving to what happens, to discuss what happens for voltage beyond threshold voltage or in the inversion regime of operation, let us change notation a little bit. In accumulation, QS is due to accumulation of holes. In depletion regime, QS is entirely from the depletion charge, denoted by QD. We saw that in the depletion regime, holes are depleted, electron concentration is increasing, but still its charge is not significant compared to the acceptor charge. So the entire QS charge is if it is coming from depletion charge. That's the reason it is called a depletion regime. So the charge contribution from the electron concentration is negligible still. And at the onset of inversion, that is V equal to VT, the depletion charge is denoted as QD inversion. So because as you increase V greater than VFB or 0, you are entering depletion region, and you keep increasing V, so your depletion charge should increase, depletion width should increase. Okay. So, and at the onset of inversion, whatever is the value of QD, you call it QD, and with extra suffix INV indicating it is QD at inversion. So thus QS equal to QD in the depletion regime. All right, and QD increases with voltage, and QD inversion at the onset of inversion. That's all. So thus the QS in depletion regime and this kind of relation minus QNA XD is actually correct only if it is depletion charge, right? Because I just multiplied background concentration QNA background charge with distance. So gives me, this is in per centimeter cube, this is in centimeter. So QS, all the charges and capacitances that we deal in this course are in units of per centimeter square. Okay. So this QS also is charge per centimeter square. All right. So you are having, you are multiplying depletion width with depletion charge. So you get total depletion charge per centimeter square. And that is equal to, if you just cancel this QNA, there will be square root QNA. So that is what it is here. So this depletion charge is there, and that is equal to Qs. Thus, Vt equal to Ψox plus Ψs for ideal MOS, and Ψox is what? Minus Qs at inversion. So the semiconductor charge at inversion by Cox plus Ψs at inversion is what? 2 phi f. And Qs inversion is nothing but Qd inversion. Okay, because entire Qs is coming from depletion charge, and inversion charge, the charge contribution from electron concentration is negligible. All right, so substitute Qd inversion from here, where Ψs you substitute as 2 phi f, because Ψs is 2 phi f. In the Qd expression, minus 2q minus square root 2q Na epsilon s Ψs, you substitute 2 phi f for Ψs. So this gives you a single expression for Vt, which is what we wanted to do yesterday, but it was already 1 o'clock, so I had closed the meeting. So this is the simple single expression for ideal MOS, and you know what is phi f. We have just seen. So now moving to lecture MOS 04 today. We have Ψs is equal to Vt ln ns by np naught. This is from Boltzmann relation. So in the depletion regime, we know that ns ranges between np naught to pp naught. So np naught means corresponding to zero charge, flat band condition, and pp naught corresponds to threshold condition. So corresponding to what? Flat band condition and threshold condition for voltage. So in this range, Ψs ranges between what? So Ψs also keeps increasing. If V keeps increasing, the drop across semiconductor also keeps increasing. And how does it increase? Using the Boltzmann relation again, Vt ln np naught by np naught, because ns changes from np naught to pp naught. So you just substitute these ranges here in this top expression, ns by np naught, you will get this. So which is what? Here np naught by np naught, ln1 is 0. So right hand side we identify it as 2 phi f. Okay, so Ψs ranges from 0 to 2 phi f in the depletion regime. So that's a potential, which is, this is also called surface potential. All right, Ψs is also called surface potential. Instead of saying all the time drop across semiconductor, potential difference across the semiconductor, it's a single word, which is surface potential. So, and in that depletion charge, and the depletion charge Qd given by this expression ranges between what? Ψs you put 0, and so left hand side becomes 0, and Ψs you put 2 phi f. It varies to this value. I have put mod because Qd is negative, right? So in order not to confuse with changing this to greater than symbols, just to retain same notation, I just put modulus. Okay. So depletion width is what? This is the formula for depletion width, and this ranges between Ψs you put 0, so depletion width is 0, and Ψs you put 2 phi f, you will get some depletion width. All right, and at the inversion, at the threshold, or instead of at inversion, I call it threshold, or at the onset of inversion. I should either call at the onset of inversion or at threshold. So at threshold, what do I have? Qd is Qd inversion, which is this right side, this limit, and xd inversion is this right side limit. So this is what I have. Now moving forward, what happens beyond threshold? So that is for V greater than Vt. In fact, from the point of operation of MOSFET, it is beyond inversion or the inversion regime of operation, that is of the most importance or interest actually. So it is the inversion regime of operation is what is of interest to device engineers or whatever circuit engineers as far as operation of MOSFET, the transistor, is concerned. So let us draw how the carrier profiles look for V greater than Vt. So I am drawing it inside semiconductor. So we have drawn it earlier. This is PP naught, NP naught, hole concentration here. Below it is electron concentration. The curves related to number 4 are nothing but V equal to V4 equal to Vt. So that is that is onset of inversion. So that is why we have NP0 going and touching PP0, and PP0 coming down and touching NP0, because NP0 NP equal to Na square. So now if I increase V to V5, so I will have hole concentration further going down, okay, because holes get further repelled, so the further hole concentration goes down, and electrons get pulled to the near the surface further, even stronger. So electron concentration further increases up like this. All right. So this increases further this way. So if you see what is happening here in terms of charge picture, so this is carrier concentration. If I plot in linear scale, you see that the holes are depleted for a very large region. This is say XD inversion, x-axis at the onset of when the carrier concentration rises up steeply in log scale. So this entire region is depleted of P, and then curve 4, if you see, it slowly goes up and then matches with this value is PP0. We have seen this earlier. So if you increase voltage further, slightly this gets shifted towards right. So you will see curve 5, for hole concentration. For the electron concentration, if you see, we know that earlier yesterday we have seen electron concentration goes and reaches PP0 value at the surface. This is 4. And 5, if you increase V beyond VT, so this is what happens. So electron concentration increases very high here rapidly. Okay, so this is corresponding to voltage condition 5, which is greater than VT. And if you see this, let us see in terms of space charge. I have not drawn space charge, but you can draw it. Rho is equal to Q times P minus N minus Na. And we know that we have seen earlier that P is much smaller than N plus Na in this region. All right. So it is negligible. So you just have rho equal to minus Q times N plus Na. Now QS is what? Integration of this with respect to just x-axis. So QS will be in per centimeters per units. And if you separate these two, N and Na separate, so I'll have one integration for electron concentration, one integration for background ionized acceptor concentration. So the integration of electron concentration, I call it as Qi. I denote it as Qi. And the integration of background ionized acceptor charge, I call it Qd, which we have seen earlier already. So this is nothing but depletion charge. Okay, so what I mean to say by depletion charge is it is the charge due to ionized acceptors. And the concentration of electrons gives rise to some charge, and I call it inversion charge. I call it inversion charge because it is electron concentration, even though it is p-type substrate is what we are seeing. So at the surface it is inverted, so we are seeing inversion charge concentration. If electron concentration means it is inversion charge concentration, and Qi is called total inversion charge, basically the integrated electron concentration. So thus QS is sum of Qi and Qd. That's what we have it here. And all are negative for V greater than 0. V greater than 0, QS will be negative. So Qi and Qd are also negative, electron concentration and acceptor concentration. So in the depletion regime, that is VFB to VT, voltage between VFB to VT, we'll have mod Qi much less than mod Qd. That's what we said. Electron concentration is much smaller. It was negligible compared to the depletion charge. Yesterday we have seen that. So that is this curve 4. If you integrate curve 4, that integration will be much smaller than if you integrate this entire area. Okay, because this is PP0, and below that in this particular area gives you acceptor charge. So that is much smaller. So however, beyond threshold, what happens is that is V greater than VT in inversion regime, mod Qi becomes comparable or even much greater than Qd. Okay, it becomes comparable or even much greater than Qd depending on how much large voltage you apply beyond VT. So what it means to say is mod Qi increases so rapidly for every incremental increase in voltage beyond VT that the increase in depletion charge is negligible compared to increase in inversion charge. So if you see in terms of the incremental values of charge, QS is QI plus QD. So for an increment of delta V, I'll have delta QS is the change in semiconductor charge, and I write it as delta QI plus delta QD. Okay. So for V greater than VT, for a change in delta V, okay, for a change in delta V, change of delta V in V greater than okay, so that is mod QD, delta QD is much smaller than delta QI. So in other words, the change in semiconductor charge is nothing but change in inversion charge. So total inversion charge is what is contributing to the change in semiconductor charge. So thus we can say that for V greater than VT, QD does not increase beyond QD inversion, which is the depletion charge at threshold. So what we are trying to say is this line, what we showed as 4 and 5, this 4 and 5 are so close to each other that the whole area, that is this rectangle area, you can say, is not going to change much if you just shift this line right side little bit for V greater than VT. That's what we are saying. Okay. So the depletion charge is not going to increase beyond the charge at inversion or threshold voltage. So QD is actually is equal to QD inversion even beyond threshold voltage. All right. So we have figured it out that QD inversion, QD does not increase beyond QD inversion. So QD is equal to QD inversion. QD is approximately equal to QD inversion for V greater than VT. So this is what we are saying. Okay. So because entire increase in voltage is taken care by inversion charge. What about field and potential beyond threshold? You have to connect it finally to voltage applied, no? So we have to, from the charge picture, we are getting back to a voltage picture, right? So so in between we have this field picture also. So you have in the semiconductor 4 corresponds to threshold, which is simply a triangle. All right. So this XD inversion is the depletion width at inversion. TS is constant electric field at the surface, semiconductor surface. So if you see, if the inversion charge, I mean the field corresponding to this particular charge picture will be like this right side gets shifted little bit, okay, and here you have a huge increase in charge, so there will be increase in electric field very near to surface, and then much of the other region it is all the depletion charge, so constant slope, so that is linearly varying, and it increases slightly here, which is almost negligible, unseen. So the red curve is for V greater than VT. All right. So you can clearly see that if I only neglect this shaded area, which is coming from the inversion charge. So that's what is written here to the right side. So area under 4 gives you voltage drop across semiconductor psi s. Okay. So if you consider the areas, okay, if you consider the areas under the curves 4 and 5, they seem to be almost equal. Okay. So area under curve 5 is only marginally larger, but it can be approximated to be area under curve 4. And that increase in area is coming mostly due to inversion charge, because the depletion charge has not changed much. Okay, so that is what I have written here. So thus integral of electric field Si, which gives you psi s inside semiconductor, does not increase much beyond the value of psi s at threshold equal to 2 phi f. Okay, so that's what is written here. For V greater than VT, QS is equal to QI plus QD inversion, and QD becomes equal to QD inversion approximately, because or since and psi s is approximately equal to 2 phi f. So two things have remained constant beyond threshold voltage. What are the two things that have remained constant? One is the inversion charge, depletion charge has remained constant, and the surface potential or the drop across semiconductor also has remained constant, both because the electron concentration is dominating, so QD does not change, and even though electron concentration is dominating, the area under electric field will be so negligible, compared to the total area. So psi s also is approximately 2 phi f. Then the question that comes follows is, then where will the extra applied voltage beyond VT drop? Okay, so we have increased voltage beyond VT, but we are saying that inside semiconductor it has not changed. It is still 2 phi f. So where should it drop across? Then we have increased V beyond VT, but semiconductor drop has not changed beyond 2 phi f. Then the excess applied voltage beyond threshold voltage should drop across oxide, because there is nothing else that we have in the picture. So it drops across oxide. So we have to calculate that also and see. So note that the electric field at surface of the semiconductor keeps increasing, because V greater than VT implies Q inversion is increasing, which implies QS increases total, which implies electric field at surface increases from Gauss's law. You see that electric field at surface has increased from this value to this value. The total potential drop has not changed because the area under the curve is negligible. Area of the shaded region is negligible, but not the actual electric field value at the surface. Okay, actual electric field value at the surface is given by the total charge, which has increased because QI has joined now. Inversion charge has come into picture now. So electric field has increased even though potential drop has not changed. So if electric field has increased, then electric field in the oxide also has to increase, because we have this continuity equation. Okay, so this continuity equation tells you that electric field in oxide must increase because electric field in semiconductor has increased. And this increase in electric field in oxide results in increase in oxide drop. And we know the formula for oxide drop, that is minus QS by Cox. So QS is QI plus QD, and you separate QI and QD. So minus QI by Cox plus QD is nothing but QD inversion, and minus QD I should write, but QD inversion is negative charge, so I write it as mod QD inversion. And if you see from Kirchhoff's voltage law, KVL, V is equal to psi ox plus psi s for ideal MOS. Then that is equal to minus QI by Cox plus this second term plus 2 phi f. This 2 is psi ox from here, and this psi s is approximately 2 phi f we have seen. And if you join these two, it is VT. Okay, so I have minus QI by Cox plus VT. And if you want to get an expression for QI as a function of voltage, you get QI as minus Cox V minus VT, because you just get QI in terms of this left hand side V and this right hand term VT. So minus QI is nothing but Cox times V minus VT. So VT goes this side and you will have an expression for QI. This expression is valid only for V greater than VT, because for QI, since we have assumed QI is approximately equal to 0 for V greater than VT. So you cannot say that I'll put V less than VT here and I'll get QI as positive. So what does it mean? So it makes no sense, because we have derived this expression only for V greater than VT, and we have assumed QI to be 0 for V less than VT. Okay, so this is how things actually look. So QS, if you plot as a function of voltage, because once we plot things as a function of voltage, charge as a function of voltage, then we can find capacitance as a function of voltage. All right. So Qs as a function of voltage, when V is less than 0, it is accumulation, so positive charge. And we saw that I have written here only for accumulation because you have seen this expression long ago, 2 classes back, right? So Qs is equal to minus Cox V. V is negative, there is a minus sign already, so Qs is positive. So, and it is varying linearly here, so I just varied it linearly. And if you plot as a function of V, you see that this QD is changing like this, increasing like this, and then it saturates beyond VT, and the saturation value is QD inversion. So this is the QD expression, QD, depletion charge, this one. It saturates at QD inversion beyond V rather than VT. And if you see inversion charge beyond VT, it increases rapidly. Actually, from this approximate formula, I should draw something like here, and I should draw with the same slope here. Okay. So, but this is only an approximation. Maybe I should do that. At least I should change. I should keep this as the same slope, because both have same slope Cox. You understand what I'm doing? Whatever. Basically, both are overlapping. Okay. So here at least two things are there. So here also let me change it, because you may get confused why this is varying like that. So it is 0, Qi is 0 until Vt, and then increases like this, linearly. So this is Qi. Okay, Qi is 0 until Vt, and beyond Vt, Qi increases rapidly. And how it increases? At a slope of Cox, which is similar to how it increases in the accumulation, because this here also you have slope of Cox. Qs is minus Cox V, and here it is as if it is shifted right just by Vt. And this accumulation and inversion are like symmetric things, but not exactly at 0 or anything. There is a region in between which is depletion. Okay, and there is a depletion charge also. And if you sum the two, Qi plus Qd, you will get this red color curve, which is the total semiconductor charge Qs. Okay, so that is what we have plotted. And now moving on to next topic, we have QV characteristics are over. So these are nothing but QV characteristics. Any doubts so far? Please ask now. It's not good to just keep silent. At least something should be there, no, to ask. Come on, I'll just pause for a while. Any questions? Because finally we have to. Okay. So let me ask a question then, if you are following or not. Okay. So what is the reason that we assume psi s to be constant beyond threshold voltage? Psi s is semiconductor drop. Okay. What is the reason? Can somebody answer? If you do not answer, maybe I will pick somebody. Hello? Because this is somewhat involved. There is no point in increasing the complexity, without you understanding. If you have any doubts, or at least you tell that you have understood. And if you have understood, you should tell, you should answer the question, right? Chandan, any doubts? Not there. Chandan Kumar Maurya. Ritvik. Ritvik. Why is everyone silent? At least whoever has understood, tell me. Even if it is wrong, it's fine. Vamshi Teja. I get a doubt whether I'm audible because nobody is responding. Very strange. At least you should respond, even if you don't know the answer, right?
It's audible, sir. Yes, sir.
Yeah. Okay. Good. So then why nobody else is? At least I expect them to respond. Vinod Kumar. This is surprising. Okay, maybe I should call every name and then see what is happening. Srinivas Murthy.
Sir?
Yes. Yeah, Srinivas. Can hear you. Hello.
Yes, sir. I'm thinking the answer.
What is the question?
Why is that voltage across semiconductor is constant even with the increase in voltage, sir?
In what region of operation?
Above threshold voltage.
Yeah, that also you should complete, right?
The voltage drops across oxide, sir. So
no. That is it drops across oxide because it cannot drop across semiconductor. It's not the other way. Susrish.
Sir, sir.
Yes. Can you answer?
No, sir.
Oh, this answer is nice. Very quick. Thank you on top of that. Great. So Bala Vignesh.
Sir, so the voltage is nothing but the area under the E and X curve, right? So that extra portion which is at the beginning, that area is somewhat negligible compared to that triangle area. So if we take the area under the curve, it's constant only. Right? Means even if we increase the voltage beyond VT.
Okay. Okay. So fine. So let me get back. At least someone is following. So let us try to understand non-ideal MOS, and then let us finish it off in this lecture. Okay, so we have got ideal MOS and everything. Before we derive CV characteristics, let us just complete the task of introducing non-idealities. So non-ideal. So non-ideal MOS junction, MOSCAP. So what is ideal? We said ideal means one condition is phi ms is equal to 0. Second thing is QF is equal to 0. So non-ideal means what is what is going to change? We have to see. Okay. So non-ideal means non-ideal means phi ms not equal to 0, QF not equal to 0. Obvious. Okay. So let us take this condition. That is first one, phi ms not equal to 0. Okay. So what it means is there is a metal semiconductor junction. If you take metal semiconductor junction, in metal semiconductor junction, the potential drop is equal to phi ms. That's what it means. So you have a semiconductor, you have a metal oxide semiconductor, and then there is another metal here. Okay, and then you have a battery applied like this, V, and we have seen earlier that drop across oxide is called Psiox. So drop across oxide is called Psiox, and there is a drop across semiconductor, and that is called Psi S. Now there is a drop across semiconductor metal also. When phi ms is non-zero, we know that the semiconductor to metal, the potential difference will be phi ms. That's what we have seen many times. So this is phi ms. So if you apply Kirchhoff's law, apply KVL in this, so what do you find? Applied voltage V is equal to drop across oxide, because the drop across metal is 0. Okay, drop across oxide plus drop across semiconductor plus phi ms. Okay, so this is for non-ideal. For non-ideal MOS. Okay, so that is one important change. You remember what we had for? Do you remember what we had for ideal MOS? This is not there. Okay, we just said Psiox plus Is. But you can ask. Okay, what do you ask? What is the charge picture? Because first of all, how is it that phi ms not equal to 0 will put some charge in the device? So that's what you have to ask, right? So because the ideal MOS capacitor, how did we define? Charge in this device is 0. Okay, so no charge anywhere, be it MOS junction or MS junction, because MS junction cannot be avoided when you talk about MOS junction. So no charge in the device means no charge throughout. Okay, now definitely when phi ms is not 0, which means the Fermi levels don't align in the semiconductor metal, so there will be some charge transfer happening between semiconductor and metal, and there will be some phi ms drop. All right, so is it that there will be charge transfer only across this junction, semiconductor and metal, and here there won't be any? Not possible, right? Because then if V is 0 here, okay, then if you travel across this whole loop, then you will find that if there is no charge anywhere between metal, oxide, semiconductor, which means no drop, then there will be only phi ms, then KVL will not satisfy. So if you put V equal to 0, and if there is a phi ms, if there is a phi ms here, if you put V equal to 0 here, there has to be psi ox and psi s. So which means there will be some charge in this MOS junction also. Without any charge, you will not, anyway, whatever be the charge in the metal, drop is going to be approximated to be 0. Okay. So in the oxide and in the semiconductor, definitely there should be some drop, because if V is put 0, psi ox plus psi s plus phi ms should be 0, and phi ms is non-zero, which means this together must be equal to minus phi ms. Okay. If V is equal to 0, implies psi ox plus psi s equal to minus phi ms. So this means there has to be charge in the semiconductor. Okay, because charge cannot be say in the oxide. If there is a charge in the semiconductor, then that charge should balance metal charge. So definitely there will be drop across oxide. So there will be drop across semiconductor because there has to be some charge, and that's how it is. There has to be some drop here. So there has to be some charge in the semiconductor. And if there is some charge in the semiconductor, the compensating charge should be in the metal. So which means the oxide, which is present between two charge, between the charge separation, right? So definitely oxide should have some drop. So that is what it is. And which means clearly MOS junction, not only MS junction has charge transfer, has charges at junction, it causes MOS junction also to have charge, to have charges. Okay, so how it is, we will not see for now. We can see later, but you can just draw the band diagram to understand what we are saying. See, this is metal, this is oxide, this is semiconductor, this is the other side metal. So let us first draw this side. Okay, so it is metal side E naught here, say Fermi level is somewhere here, and semiconductor side, if they are very far apart, so this is M. If they are very far apart, this is where the Fermi level is. This is E naught, and if EF of the semiconductor is below like this, and EV is below, and EC is like this. Okay, E naught is like this. So this is E naught, EC, and EF in the semiconductor, and EV. Now these have to align. All right. So this has, and this metal and this metal here are connected. Okay. So I should draw the Fermi level here also as EF. I'll have to draw at the same level because voltage drop is 0. I can say what, for V equal to 0. I'm drawing. So this and this Fermi level should be aligning. So this here they should align. Okay, they should align here. So this is left hand side EF. This is E naught. Okay, so I will fix this E naught. There is not much drop in the semiconductor, in the metal, so I'll just keep it continuous up to edge of metal region. And now I have to push this up. So the semiconductor bands go up. Okay, why? Because you have to match with EF here. Okay, so so EF goes up, so you will have, so this is EV. So when EF goes up, EV will become like this. So this is what EV is, and this is EF aligns. And if this EC also will bend, start from here, and then it will bend like this. So this is EC. And E0 also will bend like this. All right. Now we have seen that. Now on the left hand side also there is no potential drop in metal. So metal E0 I will draw, which is at the same level as this E0. So this EF is same level as this EF. Now what happens here? So if only I draw E0 constant like this, and then EC constant like this, EV constant like this, which means there is no charge in this junction. Okay, so there is so if I have to draw E0 and merge with this, it means there is a E0 derivative should be field. Then if there is no charge in semiconductor, there should not be any charge in here or this side of the metal, then how can we have a field? Okay, it is not possible. So this is not a correct picture. Bands have to bend here also. In what way they have to bend? Definitely you have to merge this E0 with this E0. So some drop will be like this in oxide, and then it will bend like this. So this much of bending will be there. This corresponds to what kind of charge here? This corresponds to depletion, which means here you will have negative charge. So here you will have means definitely you should have positive charge, and positive charge to negative charge field should be there, and slope of E0 is positive here, so which is correct. So here also you have negative charge. On metal side you have positive charge. It is like this junction and this junction, they look the same. You know, if you flip it, if you take this SM junction, you flip it, you get this MOS junction. Okay, instead of drastically E0 going down and merging with E0 of M, it goes smoothly because you have introduced an oxide which takes some potential drop. So this is how it will look. So there is some charge here in the semiconductor. All right. So clearly here what we have taken is phi ms less than 0, because negative charges, because EF actually we have taken above EF of semiconductor. So phi ms here is phi ms is less than 0 here. Okay, so that is why semiconductor is negative and metal is positive and phi ms is negative. Is it clear? So this way this V gets modified. Then what we have to see is, sir, for flat band, what should I do to make bands flat in the MOS junction? Of course, you can. This will not change even if you apply bias. Why? Because if there is any change that happens here, which means this junction will not be in equilibrium. So it will conduct. It will carry. It has to carry some current. So even if you apply bias, so here how we wrote phi ms even under the case of bias, because we know that there should not be any change in potential drop here even under applied bias, because if at all there is any change in potential drop here other than phi ms, it will start conducting, and which is not possible because there cannot be any current through insulator oxide. That is the reason we fixed this potential at phi ms even though we have applied battery and all that. Okay, so that is one thing. So what is the voltage that I should apply so that these things will be 0, psi ox and psi s, there should not be any charge. So what I'm trying to say is I should calculate VFB and VTB, right? VFB is what in this non-ideal case, VT is what in this non-ideal case. So that's what I should find out. So how do I find out? VFB condition is implies flat band in MOS junction. Flat band in MOS junction implies psi s is 0 because bands are flat means psi s there is no drop across semiconductor. If there is no drop across semiconductor, implies QS is 0, implies oxide drop, implies psi ox equal to minus QS by Cox is equal to 0. Okay, so PFB flat band in the sense MOS junction, flat band in the MOS junction, that's what it means. So flat band indicates psi s is 0 because bands are flat. If only there is variation of EC or E0, okay, then that means there is a potential variation. Otherwise, there is no. So flat means psi s equal to 0. If bands are flat, then charge also will be 0. Okay, so which means psi ox also is 0 because QS is 0 and psi ox is given by this relation. So psi ox is also 0. And from the case of from the equation KVL, which is like V equal to psi ox plus psi s plus phi ms. Okay, so the voltage that I should apply, so VFB is the voltage that I apply across battery to make bands flat. So which means psi ox is 0 and psi s is 0 and this phi ms will not change. So this is what it is, implies VFB equal to phi ms when phi ms is not 0. And backward compatible because if phi ms is 0, VFB is 0, which is what we have seen. What is VT? I will tell this VT condition with the VT expression, and then we will discuss the second case of non-ideality in the next class. So Q, which is the QF not equal to 0 case. Okay, this case we will discuss in the next class. We'll finish what is the expression for VT here. So VT expression is what? VT is the applied voltage. VT is the applied voltage. So again, start from KVL, V equal to psi ox plus psi s plus phi ms, and VT is the applied voltage. So psi ox inversion plus psi s inversion plus phi ms. Okay, so clearly VT is, and psi s inversion is, it is same 2 phi f, it will not change. Okay, that's what it is. It will get inverted. Okay, implies QS inversion is nothing but QD inversion. Okay, implies psi ox at inversion is same. That is not going to change because psi ox is nothing but psi ox at inversion is nothing but QS minus QS at inversion by Cox. So this is nothing but minus QD inversion by Cox. Okay, so this has not changed. So implies I have VT as minus QD inversion by Cox plus psi s inversion is 2 phi f plus phi ms. So that's just this phi ms gets added. That's all, nothing else. Okay. Okay. If there are no doubts, I'll close the meeting here.
Excuse me, sir.
Yeah.
Sir, why vacuum level of semiconductor oxide and metal are different?
Where?
In the
Before
above band
connecting
diagram.
or in this? This
No,
picture?
no, sir. Yes, sir. In this picture.
Yeah. See, before connecting, we put E0 same, right? Throughout. Before joining them, E0 is same throughout. MOSM. E0 is constant. E0 is 0 just outside metal, just outside oxide, outside semiconductor. So E0 is reference is 0. But when you bring them together, there will be charge transfer between various junctions. So when there is charge transfer, there is a field. So even if you have an electron just outside the regions, outside the materials, there will be field even outside. Okay, so good question. I don't know. I mean, this should come even before PN junction, right? I mean, even the discussion of PN junction, let us just take this PN junction. Okay, so I have a PN junction like this. Let us say we draw only fields in one direction, right? Because saying that it is one-dimensional situation. But if you take a finite cross section, okay, and then if you go from here to here, inside two materials, you will have built-in potential. Is it yes or no?
Yes, sir.
Who is that asking, by the way?
Abhay, sir.
Abhay. Abhay. So if you go from 1 to 2, within the semiconductor, okay, you have a field from N to P. So there is a potential drop from 1 to 2. Okay. Imagine the semiconductor cross-section area is A. Area is A. Okay. Less than infinity. Okay. So it is not infinity, finite. Okay. A is finite. Now what happens is there is a region outside PN junction also. So if you, which is what we talk about as electron vacuum level, right? Vacuum level is what? The energy level right just outside the semiconductor, okay, or even metal. Okay, you have a semiconductor or metal or whatever crystal you have, and there is a potential energy of electrons within that crystal, which is the conduction band. But if you take that electron out of the influence of all those nuclei, you will say that its potential energy is zero outside. Okay, so here potential energy is zero. Here inside potential energy is less than zero, and PE potential energy zero corresponds to vacuum level E naught. Okay, potential energy zero corresponds to vacuum level E naught.
Okay.
Okay. Now, if you take this 1 to 2, you go, and if there is a finite area of cross section, and you go out and come, say you travel like this and then come. If only there is no electric field outside, when you go out and come back, will there be any drop? If say, let us say there is no electric field outside, will there be any drop? So what I do is I take an electron just outside semiconductor like this, and then travel like this outside semiconductor, and then come back inside. Okay, if there is no field outside, what will the potential drop between 1 and 2?
It will be zero.
It will be zero. But how can you have one potential difference 1 and 2 if you travel this way, and if you just change your path, you will find a different potential difference or what? It is not electromagnetics. It is just simple electrostatics. So your psi also should be same, even if you take a different path. So definitely there is an electric field outside, right in vacuum. So electric field outside means what? E naught, the potential energy of electron is changing. So right outside the semiconductors, there will be fields. If there are fields inside semiconductor, there will be fields just outside the semiconductor also. Very far from the semiconductor, they will die down. But E naught is potential energy just outside the semiconductor. So field will be there just outside the semiconductor. So E naught will be bending. Is it clear?
Yes, sir. Sir,
Okay.
like conductor, like in conductor we have electric field inside the conductor is zero, and charges are only present on the surface. Like,
Yeah.
is it the same? Is it the same in semiconductor also?
No, that is electrostatics case. Okay, in electrostatics, there will not be any field inside metal. All fields go on the surface. But metal wire you connect and you connect a battery to a device. So electric field inside is not zero. Only current will flow inside a metal wire only if electric field is there. So electric field is not zero inside metal. It is there if you have a current flow. And inside semiconductor, electric field can be there. You can have current flow. And if you don't want a current flow, still also you can have electric field, because the drift and diffusion balance each other sometimes. So you can have electric field inside, but with zero current also in semiconductor, because you can have gradient, and which causes diffusion current. Okay.
Yes.
So
Okay, sir.
don't think conductor means zero electric field always. It is only electrostatics, not dynamics or when you have current flows.
Okay, sir.
Okay, I'll end the meeting here.